You already had a couple of talks this morning, and so I'm not talking too much. I have you work a little bit. I put the question up here, and I'd like you to give me some input. What is snow instability? That's
an avalanche.
Thinking. Doug says avalanche. So what do we need for an unstable snowpack? What is an unstable snowpack? Just throw in some words.
A slab on top of the weak layer.
Ah, here we go. So that would be a good weak layer, I guess. Pretty porous, looks pretty fragile. Some surface wear. And on top of that, we want to have a slab. And as Andrew says, it's not only the weak layer, it's the slab and the weak layer. We have a couple of tools how to figure out the stratification. You see some guys here digging. There's somebody here in the back doing a profile. There's some tests being done here. And you see they get out the SMP, do measurements across this little field. And these guys who are digging here, they are actually my colleagues that I discussed with a lot in the past years on this topic of what is snow instability. And yeah.
Is this just an average day in Switzerland?
It's pretty cloudy though. So you see there's a lot of work involved, and at the end of the day you have to close the hole, and this is the happy crew. And this is Joan, this is Jörg, Alec, and myself. And I also want to thank them because they helped me a lot discuss here, and they also helped me digging. You've seen already some instruments that you can use to figure out the stratification of the snowpack and to learn something about snow instability. And for the following, I have to introduce to you two data sets. So keep in mind, we have a Reuter block data set and we have a propagation saw test data set. Reuter block, everybody knows, it's this big Swiss block they used in the Swiss military. They still use it. And somebody jumps on it. So you have some scores there. So it's not a metric scale, it's an ordinal scale. There's some jumps in between. And for propagation, for the propagation saw test, what we measure is the crack length. So that's a metric scale. We have a length in meters or centimeters. With these two data sets, we don't only have the tests, we also have SMP data. And also we have traditional snow profiling data. And the SMP records a penetration resistance signal that we can actually match very nicely with the traditional profile. And also for all of these data, we have information on signs of instability. So we actually looked at the slope, whether we skied it or it came down or it didn't come down, or we had some cracks or some booms. We had all these observations. So let's go to the first data set and try to understand what failure initiation means. And I start right here with these terms, failure initiation, later will be crack propagation. These terms, you all know them. And these terms, they will help us to describe snow instability in the end. So we start with failure initiation, and one way to model failure initiation is a strength of material approach, and you would use the stability index. The classical stability index, where you have a strength, in this case the strength of the weak layer, color red, and you want to compare to the strength of the weak layer, you want to compare the stress that this weak layer feels when a skier is on top. So you can put a force on top here, but actually you need to know the properties of the slab to model the stress that this weak layer feels down there. So that's why I put here all these properties that you need to know of the slab to calculate the stress down there. And this is what it looks like. This is the shear stress in the slab and here in the weak layer that would be caused by a load on top. And if you would flip this Reuter block here and make it level, you would still have shear stresses. So that's a way to calculate failure initiation just by the stability index. So we call this thing up here, for this talk, we call it failure initiation criterion. And now we can compare this model value to our Reuter data set. And you see here the Reuter scores from 1 to 7. I just pulled 1 and 2 and 6 and 7 because they're pretty rare, these observations. And you can see it increases. Yes, we got a good criterion. So then we need something to describe crack propagation, and I already said we could use the critical crack length. So how do we determine the critical crack length? The critical crack length is actually not so easy because you have this big block and this block bends. But just as a rough equation here, I just put the ingredients for you to remember what we have to consider to model this critical crack length. And we actually need to know the fracture energy of the weak layer, which is a property of the weak layer. We can also call it the strength. And we also need to know the load of the slab on top. So if we know the load of the slab and the weak layer fracture energy, we almost know everything. One more thing that we need to know is how this thing on top bends. So how much deformation you have here during the onset of crack propagation. And this is the E, the elastic modulus. And I wrote here E slab, because this E slab is not the modulus of the layers. That's a different thing, because snow, yeah, it has these layers, and it's like a composite, so it has layers, and the effective modulus that results in the effective bending that you see is a superposition of these layers, and you have to calculate this value. So to describe crack propagation, we actually have these ingredients. So how much does it bend, how fragile is the weak layer, and how much load do we put on top? So now we can also model the critical crack length. And here there is the model value, and there is the measured value for the second data set that I mentioned at the beginning, the propagation sort test data set. And you see, that doesn't look so good. But here, I did neglect the layering. So I just talked about it. This modulus, or this deformation that you see, you cannot get this deformation right if you consider an average modulus. You need to consider the real effective modulus of the slab. And if you do that, it lines up pretty well. You still have some error because it's a model, it's live, but you get closer to the 1-1 line. Okay, so now we got two criteria. We got one criterion for initiation, one criterion for propagation. So let's look what we can do in terms of validation. Down here I put the failure initiation criteria, and here I put the critical crack length, both modeled from field data measured with a snow micropen. And for all these graphs now, it's maybe easy to think that here in the corner, the low values of both criteria are rather unstable, and the more you move along the axis, the more stable it gets. So the further you move on the scale here on the axis, the higher the crack length is. Yeah, the higher the crack length, the more stable. And the same for the initiation criterion, the higher the values, the more stable. And actually, if you compare it to the signs of instability that we observed on these slopes, you see that signs of instability mostly appear here in the lower left corner. So either there were all signs present, so avalanches, shooting cracks, and booms, that would be red, or they were just booms, or they were just cracks. They're mostly down here, but you have some white spots in between. So we can do some validation. We can see how well our model performs. In other words, we try to predict. And Ron already pulled up this confusion matrix that is a little bit confusing. And to make it even worse, I flipped the axis. When I seen Ron's talk, I said, maybe I should just try and change it. So I have prediction here, and I have observation on the other side. So prediction, this is our two criteria here. Now we can just have thresholds. We can just say, okay, if failure initiation is below 200, and if crack propagation or the critical crack length is below 0.3, that's unstable. So this would be the prediction. And stable would be no signs of instability, and unstable would be signs of instability. So what do we want in this matrix? Ron mentioned it already. We want to have a high accuracy. We want to have a high number of, or a high probability of detection, and we want to have a high number of predicting the non-events. And as we're here talking about snow instability, and I'll tell later why I like this word instability better than stability, we are actually, with probability of detection, we're actually looking at how many unstable cases can we predict. So unstable prediction is this, these cells here. So actually we're talking about this number here in the back. How many unstable cases do we get right in comparison to the ones we miss? And probability of non-events, that would be how many stable cases do we get right in relation to the numbers that we miss. So now we put in the numbers and we see actually we're doing pretty good with the probability of detection here. So the unstable cases, we got them quite under control. But the stable cases here, we're getting many stables, but we also have a lot of false alarms. We have like 30 cases here that we say they're unstable, but they're actually not. And those are the white dots in here, or the circles that don't have any color inside. That's why we're having 65% and not a higher number. So this is what we're working on in this talk. Trying to massage the data here a little bit. No, we're not massaging the data. We're actually coming up with a new idea. So I looked at these dots there, at these, sorry, I was too fast, at these points here that are in the lower left corner, and I looked in my data set and I found out that many of these false alarms here actually have partial fractures in the tests. And here I made now in all these cases there is a little dot inside of the circle where we have a partial fracture. I use this term partial fractures because I'm talking about root blocks and propagation saw tests. In propagation saw tests there would be a slab fracture. So what do I mean with partial fractures? So let's look at the propagation saw test. I hope you can see it. There is a saw moving here in the weak layer. And there you see the crack. So that's a slab fracture. And in the root block, there would be a release only below the skis or a release of only an edge of the root block. So now we got to model these slab fractures. And we actually have, for these slab fractures, all the data because we have a traditional profile, plus we have the SMP data on the stratigraphy. And if we take this data and throw it into a finite element model again, we can actually model tension and compression in the slab. So the red arrows, that would mean that the slab is torn apart, and the blue arrows, that would mean that the layers are pressed together. If we do that, this is what it looks like for this case. You see the slab is highly stratified. There's some crust here, and there's some softer layers on top. So this looks pretty complicated, doesn't it, compared to this easy picture? So what I learned from these models here is the crack can start anywhere in here. It probably starts where the stress is high. But if the layer is also very strong, it might just start adjacent. But it's not so likely that it starts close to the weak layer, because there you rather have compression, and up here at the top of the slab you rather have tension. But it's not really clear yet where this tensile fracture that we see in the slab fractures in the propagation saw test, where that really starts. So what I did then, I came up with another criterion that is again strength of material approach, I compare the average strength of every layer here that you see to the maximum stress that I modeled. And if this ratio is critical, that means between 0 and 1, that would give here a red part on the graph. And then I just take this length and compare it to the total thickness of the slab, and you get a ratio of what part of the slab is actually critical for a tensor, or critical for a tensile fracture. So let's go back to this graph. You remember failure initiation, crack propagation, and the circles with the dots inside, those are the cases that have partial fractures. So now we apply the third criterion, and if you look closely to these points here, some of them, they will move to the back. So we actually introduced a third axis now.
So I have a question just on the PST.
Yes.
Because you keep referring to anything more than 0.3 meters as being, you putting that in the stable. Anything less than that is unstable, but what we use is 50, half of the slab.
Yeah.
How did you come up with 0.3?
This 0.3 is just based on this data set.
Just from that data set, okay.
But I need to say that our guidelines are different from your guidelines. So in Europe,
Not our guidelines.
we got to work on your guidelines. So what we are doing is we're cutting the edges in a different way, where our blocks are a little longer, and we actually found out 2016 in a paper together with Carl and Alec that these propagation saw tests, they need to be longer than we thought. They need to be, and that's a bit bad actually to say it this way, but they need to be at least 3 times the length of the cut length. And the cut length is something we don't know in the beginning when we do a propagation saw test. Great, isn't it? So you do a propagation saw test, and then you see, the test was too short, so I have to do another one that is longer. And also we have some constraints for the slab thickness. So that's probably why we have different values here.
Okay.
Okay, so back to this slide. We apply the third criterion. We have one axis, a second axis, and now we go in the third dimension. So we shift these values to the back, where we model a tensile fracture. You can see the dots are now smaller. It's not so good to see. I will show you soon a little video that actually flips this cube, and you can see inside the cube. But let's have a look at the numbers first. So what are we doing here? We're actually pulling down this number of 30. We're actually reducing the false alarms, and as in real life, you can't do this at no cost. So we're also increasing a little bit the number of the for stable predictions. But in the end, we increase the accuracy, and we considerably increase the PON, the probability of the non-events. So we're decreasing the false alarm ratio. So let's have a look inside this cube. And you remember this is the lower left corner here for, with the failure initiation, the crack propagation criterion. And now we can also look in the back, and you can count these 7 cases here that are unstable, but actually they are stable. So what does this model do? It actually helps predicting instability, and it pulls down the number of false alarms. So these thresholds that we now had there, this 0.3 that Doug just asked about, and the 200, these values are just true aligned because of the colors that I seen on the graph there. Let's do some statistics now and see how well these models really perform. And statistics for models, it can be done in rock space, so it's a receiver operating curve that we're looking at. And here on this line, on this axis, you see the true positive rate, which is nothing but the probability of detection. And here on that horizontal axis, you see the false positive rate, which is 1 minus the probability of non-events. That means the best model would sit up here. So you want to have a high number of probability of detection, and you want to have a high value of probability of non-events. But here it says 1 minus. So that would mean a low value on this axis here. So we do look at different models, and we increase the complexity. We start with a model that only considers failure initiation. So basically a stability criterion, classical stability index, strength over stress. So this is how it looks like. What we do here, when we would walk on these steps here, on these stairs, what we would do is we increase the value, the threshold of this criterion. And it starts off pretty steep, but then it levels off. So when we increase the value in the beginning, we still capture all these, we still have a lot of unstable cases, but the higher we choose the threshold, the more false alarms we get, and the more stable cases we're actually missing. So a perfect model that would come up with a one threshold that is perfect, that would look like this. Tuck, tuck. So you see, actually, if we go through our data set and we increase the threshold, so when we walk on these stairs, we're not getting to the perfect threshold, because immediately when we increase the threshold, we're actually always getting some data of the stable cases wrong. So now that would be the threshold of 155, and this is the threshold that would be chosen with a classification tree. And this area that you see here under the curve, this area here is actually a good indicator of how good the model is, how well the model is doing. And this is the area under the curve, the AUC, and this is 0.8. So now let's put in the other models. Now we use failure initiation and add crack propagation. So we have these two criteria that we had on the horizontal and the vertical axis. And you see it's getting a little better. We're actually moving a little bit towards the left corner here. So this would be the perfect point. The perfect thresholds would be up here on this stair. And now we use the third model, and you can see we're actually not moving that much towards the corner, but the area is getting bigger. So this is actually a statistical indication for a three-step model approach, that this three-step model approach works better than having only initiation or only initiation and propagation. But now we got another criterion. We started off with the stability index. Then we added crack propagation. Now Ben says we also need tensile support. So in 2 years, then we have a fourth and a fifth and a sixth, or where are we going here? So I want to look at that with you, and I want to go a little bit back in time and think about what we had at the moment. And maybe you remember this table here that Jörg and Bruce presented, I think on an ISSW, it was later in a paper then, and they said there are simple observations that we do when we're traveling, and there are the bumps, the shooting cracks, the recent avalanching. Maybe we see cracking at the skis, or we can do the ski pole test. And now take a moment or two and think about what information you get from these observations. What observation gives you information about stratigraphy? What tells you anything about initiation? Which ones to tell you something about fracture propagation? Yeah, obviously it's the first three that do really have some information about stratigraphy, initiation, propagation. And this is also the reason why these three are here, why we call them the signs of instability. And what we did in this presentation so far is actually we gave a proof that that's true. We actually graphed the signs of instability with initiation propagation. And this table that we're all used to gets actually some support by this data here. Now if we think about the avalanche release 101, then this is the slide that was up on the ISSW in 2016. This is the current state of knowledge, of our understanding of how avalanches release. We're actually mainly looking at initiation propagation. So there is a damage process in natural release, and there is a skier kicking in here in the artificial release, or an explosive kicking in here and forming an initial crack that then starts to propagate. But here, there's like a boundary. We don't go beyond with our tests and our observations in the field. But we all know that even if there's initiation propagation, we might not get the most incredible avalanche, because there is something beyond here. And this is actually where current research is directed towards. Current research tries to understand dynamic crack propagation and also the confinement of slab avalanches. And this criterion that I suggest here, this is trying to go a little step into this direction, into the area of crack propagation. What do you need? How does the slab need to look like to support this crack propagation, this crack running in the weak layer? There's one more cool thing with these models, and this is something I also want to share with you. Now that we have all these data and all these criteria, we can actually look at what snowpack properties favor initiation and what snowpack properties hamper propagation. And so I pulled up the graph here that I already showed you with the failure initiation and the stress bulbs below a skier. And if I look at the data here that I showed you, and I put the failure initiation criterion on the vertical axis, and I put slab thickness down here, you can see an increase. So that means that the slab thickness has a control on failure initiation. So the thicker the slab, the less likely it is to initiate a failure. So if the slab is like 0.7 or 0.8, I have some data points up here, but they have a pretty high failure initiation criterion, so it's not very likely. Nothing new, we all know that. And also the strength of the weak layer plays an important role. So for failure initiation, those are the two things that we should think about. How fragile is the weak layer? How old is the weak layer? What grains, what size, how does it look like? And how thick is the slab? And I'm not talking about density, I'm really thinking about thickness, because the thicker it is, the more it attenuates this stress of the skier or the explosive. Let's look at crack propagation. He said it's a lot about bending. So I graphed the critical crack length and the modulus. The modulus, a value that describes the bending. The higher the modulus, the less bending, the less energy the slab provides to drive crack propagation. And again, you can see here a control of the modulus on the critical crack length. So the stiffer the slab, the less likely it is that a crack starts. Not saying that the crack propagates. I'm saying that it's the onset of crack propagation. You need a lot of deformation energy to start this propagation. And the fracture energy, we can also say the strength. The higher the strength of the weak layer, the less likely it is that the crack, or the harder it is to start crack propagation. So in terms of crack propagation, how stiff it is, how stiff is the slab, and how fragile is the weak layer. And now let's look at the tensile criterion, the third one. Again, slab thickness plays a role. Thicker the slab, the more likely it is to propagate over a long distance. So that's a little bit inverse with the failure initiation criterion. To initiate a failure, you want to have a thin slab. It's easier to initiate in a shallow spot, but then to propagate over a long distance, it's better. It works better if you have a thicker slab. Here, this is the density in the color, and there is no relation in my data set with the average density. I think this is because it really depends on the layer and on the layering, and in my data set the slabs are really, really stratified, so the average density is not a good proxy. But probably single layer densities, if you would do statistics with single layer densities, I guess it would be significant. Again, an indication, or again, probably the layering plays an important role.
Can you go back to that
Sure.
slide real quick? What threshold did you use when you were modeling there for your tensile criterion?
I use 0.4. But this.
And how would you describe that to a layman person? What does that mean?
So I'm actually using a ratio